Let's dive straight into a deep architectural analysis of OpenClaw. We are going to systematically unpack exactly what this gateway is built to do, analyze its multi-channel deployment use cases, and really get into the weeds of some recent engineering commits, optimizing its internal state management and security.
To set our baseline, let's look at the strict technical parameters. At its core, OpenClaw is an MIT-licensed open-source gateway designed to run natively on any operating system. Functionally, it acts as an agent-native bridge, connecting various chat interfaces directly to underlying AI models. For the technical requirement, you need at least Node 22 LTS to run it, though running Node 24 is highly recommended to get the absolute optimal execution performance. Our roadmap for this explainer covers the OpenClaw gateway purpose, multi-channel deployment use cases, architecture and multi-agent routing, innovations in event compaction, plugin hardening and security, and finally, performance and CI optimizations.
Section 1. The OpenClaw Gateway Purpose, Unifying AI Access.
The fundamental architectural ideal behind OpenClaw is highly focused, one gateway. We are talking about a single, unified process running directly on your own hardware. The absolute crucial advantage here is data sovereignty. By centralizing the routing logic locally, developers can entirely bypass third-party hosted services. That means you retain absolute, uncompromising control over your messaging payloads, your authentication tokens, and the memory of your agents. No data leaves your ecosystem.
Section 2. Multi-channel deployment use cases, mapping the ecosystem.
The sheer breadth of this abstraction layer requires a closer look. You have one single gateway seamlessly handling built-in channels like the local control UI sitting on port 18789. Simultaneously, it is managing bundled plugins for decentralized protocols like Matrix and Nostr, alongside external integrations requiring completely distinct API handshakes. Think Discord, Slack, and Signal. It even stretches out to support dedicated iOS and Android mobile nodes, routing complex inputs like canvas drawings, camera feeds, and voice data right back to the central hub. The true engineering achievement here is maintaining uniform data structures across all these wildly fragmented external APIs.
Let's trace the exact data flow of a request to see the mechanics in action. Step 1. The designated chat app or plugin interface ingests the user's message payload. In Step 2, the gateway intercepts that payload. It acts as the centralized brain, applying strict session management rules and calculating the optimal multi-agent routing path based strictly on the sender's context. Finally, in Step 3, the gateway securely executes that parsed request against the target. If you are running the default local setup, that target is the bundled Pi agent.
Section 3. Architecture and multi-agent routing, managing state.
State management is arguably the most critical vector when dealing with multi-agent routing. OpenClaw handles this by explicitly offering two distinct paradigms. First, workspace isolation. This approach tightly groups your agents, tool usage permissions, and context boundaries within a defined organizational structure. It is tailor-made for enterprise deployments where whole teams need shared access to a specific suite of tools. Conversely, we have per-sender sessions. This paradigm strictly isolates memory and conversational context down to the individual user interacting with the gateway. If you boot OpenClaw right out of the box without modifying the openclaw.json file, it defaults to these per-sender sessions utilizing the bundled RPC Pi binary. This prevents any context leakage between different users messaging the exact same locally hosted model.
Section 4. Innovations in event compaction, diving into asynchronous performance.
Let's analyze a specific GitHub commit merged under pull request 7665.1. It reads, fix mark plan compaction event delivery fire and forget. This represents a highly strategic architectural shift in the codebase, and understanding it requires looking at the underlying mechanics of the node environment.
Compaction is the process of summarizing historical message context so it actually fits within a large language model's token window. This is an inherently intensive operation. Previously, executing this synchronously ran the risk of holding up the entire queue. By implementing an asynchronous fire-and-forget execution model, the engineering team has explicitly decoupled this compaction delivery from the primary thread. The result is that it completely prevents I/O blocking in the node.js main event loop. The gateway can trigger the heavy compaction task and instantly return to routing new incoming messages. That vastly increases overall throughput and reliability, especially when the system is under heavy concurrency.
Section 5. Plugin hardening and security, focusing on dependency management.
Exploring the repository activity further, two vital security commits directly address vulnerabilities inherent in the Node package ecosystem. The first focuses on pinning npm plugin installs, and the second tightens the diagnostics around shadowed installs.
The remediation strategy here tackles a very specific, dangerous vulnerability: unpinned npm packages allowing for malicious drift. If you allow a dependency to update dynamically without explicit verification, a supply chain attack could easily inject rogue code into an otherwise trusted package. To absolutely prevent this, OpenClaw now forces strict pinned versioning for all plugin installs, guaranteeing cryptographic certainty for every dependency. Furthermore, defensive diagnostics have been added to specifically target shadowed installs. This occurs when a rogue or duplicate package attempts to override a core directory. The system now immediately warns system administrators if this structural anomaly is detected, effectively neutralizing the override attempt before any malicious code can execute.
Section 6. Performance and CI Optimizations. Analyzing boot times and testing. These recent adjustments drastically refine the operational efficiency of the gateway lifecycle. Trimming Startup Watcher imports directly reduces the initial memory footprint, which facilitates much more rapid boot times. Additionally, deferring early maintenance tasks ensures the gateway actively prioritizes immediate socket availability over running background cleanup during initialization. Stopping lazy cron startup triggers during hot reloads is also a massive quality of life improvement for developers. It prevents the entire system from dragging or locking up because background jobs were repeatedly firing while editing code. On the back end, splitting slow continuous integration shards ensures the automated testing pipeline remains incredibly agile. It allows contributors to validate massive architectural changes without bottlenecking the entire repository.
We have constructively analyzed the multi-channel mapping, the asynchronous event compaction, and the rigorous dependency hardening currently driving OpenClaw. It is abundantly clear that this architecture prioritizes absolute local control and non-blocking performance above all else. Which leaves us with a highly compelling question to consider. As OpenClaw continues to aggressively scale this decoupled, self-hosted infrastructure, what legacy centralized AI bottlenecks will developers systematically eliminate next?